Okay, so welcome to lecture 8 for this PYL 102. So today we'll be discussing about the velocity and effective mass of block electrons, right? So what we have seen is that energy versus k, there is a dispersion relation. Is very interesting. So the dispersion relation shows that the energy is not continuous, right? So they are obviously in the free electron case energy is discrete corresponding to the discrete k values, but in this case for the block electrons, so remember these electrons which experience this periodic potential, they are also called block electrons because they are defined by the wave function block given by a block, right? So block function, so therefore these are also called block electrons or band electrons, meaning is the same. Okay, so now what you see here is the energy is actually discontinuous at the zone boundary. So that's what you have learned from the last classes, right? And the energy curve flattens at the zone boundary, right? And also actually at the zone center. So k equal to 0 is called the zone center, and k equal to pi by a is the zone boundary. So now let us try to find out the velocity. What happens to the electron velocity? Does it depend on the band, on the energy band? Okay. Now in the free electron picture, E equal to h square k square by 2m, right? And the group velocity of electrons is equal to del omega del k, right? So I hope you remember the distinction between phase velocity and group velocity, right? So we are discussing about the group velocity of the electrons, right? Del omega del k, right? And for free electrons, E equal to h cross omega. So from there you can determine that group velocity, right? Here in the band electron, this becomes very interesting because you see that group velocity is is equal to del omega del k, right? So which is equal to del of del k, right? And omega is e by h cross, since e is a function of k, so therefore I'm writing e k by h cross, and so therefore the group velocity becomes 1 upon h cross and gradient of e, right? In k. So so that means group velocity is given by, in one dimension it will be, let's say, del e de dk, right? Or dkx, for example. Okay, so from this relation what we find, if you now calculate, so in this plot I'm showing so the plot is not very nice, but I hope that you can understand. The top plot is the energy, right? And the bottom is the velocity, right? Somehow I'm seeing that due to the conversion from one system to the other, or from the format, so there are some changes in the figure also, in the PDF figures that I have taken from some book. So anyway, so the top figure is the or the energy versus k, right? X-axis is the k. For the first figure, top figure, the y-axis is e, and for the second figure, x-axis is same, right? That is the k values, and y-axis is the v, which is the phase velocity, the group velocity. Now if you differentiate these, so what you see is that the group velocity is 0 at the zone center, right? Because the curve is flattened here, and also the group velocity for the electrons is 0 at the edges of the Brillouin zone, at the zone boundaries, right? So at both pi a and minus pi a, which are the k values at the zone boundaries, right? So you see that the group velocity of electrons is 0. The other interesting point is that there is a maxima or a minima where if you keep applying the field along the same direction, the velocity is decreasing, right? So if you increase the field, but velocity would still decrease at those points, right? Okay, so so that means the group velocity decreases with increase in energy beyond the inflection point, right? So in the energy versus k diagram, the inflection point is where you have the maximum, right? So even though the electron's energy increases, right, the group velocity decreases. So now try to think about if it is true for free electron case. I would like you to think about that. So what happens for the free electron case? Okay, think about that. All right, so this is an assignment for you to think about. Okay, now let us consider, so once you know the group velocity, which behaves in a particular way, because these are the band electrons, right? Because these are the band electrons, what you see is that there is an inflection point, and for the inflection point, even though beyond the inflection point, even though the electron's energy increases, velocity t still tends to decrease. So that's an interesting point. Now what happens? Let us consider an external field acting on the band electron. So I'm giving external field as F, electric field, right? Usually you give it use E, but since we are using E for energy, so that's why I'm writing external field as F for the acting on a band electron. Now the energy gained by an electron in time delta t would be delta E, equal to this force, which is EF now, times B times D, where B is the group velocity of the electrons, right? So delta E, then we can write it as the delta E, we can write it as d dk times delta k, right? So this we can, since we know that know the relation between E versus K, right? So that we can write it as H cross B delta K, right? Because from velocity we have found that relation, right? So group velocity is 1 by H cross dE dk. So therefore dE dk equal to H cross B delta K. So I hope that you get this point. So now from these two relations, within the limit of delta t tends to 0, what we find is that H cross dk dt will be equal to EF, right? So you equate 1 and 2. 1 and 2. Sorry, this would be equation number 3. Then you find out is that H cross dk dt and dk dt will be equal to EF. What is EF? EF is the force, right, acting on due to the field F, acting on the band electron. All right. So band electron. So now we can write this dV dt, right, as 1 upon H cross d dt of dE dk, right? Because we know the v, right, group velocity is 1 by H cross dE dk. So dV dt is this 1 by H cross d dt of dE dk, and so this will be equal to d2E dk square, right, and dk dt. So I hope that you get this point, right? So this will be equal to, then the rate of change of this electron's group velocity will be given by 1 by H cross d2E dk2, and dk dt we have found out from here, right? So this is EF by H cross, right? So this we are putting it here. Then so EF is again the force, right? So this is force will be equal to H square times this 1 upon d2E dk2 dV dt, right? So now what is this? Basically we are writing it force on the acting on the electron, right? So there is this term within the red square, and which depends on the energy, E versus K, right? And then there is a dV dt term, which is basically the acceleration term, right? So if you know that from your classical equations, you know that the force is mass times acceleration. So that means this is equivalent to the electron mass, right? And this is called effective mass of electrons, right, which is given by m star, and m star is given by H square by d2E dk2. So what it means is that this effective mass of an electron, right, is dependent on the band structure, right? How the energy of the electron behaves as a function of k values within the Joule zone, right? So effective mass depends on that. So you may remember that in the initial classes I had mentioned to you that we are considering free electron mass at this point, but electrons in the solids they can have different masses. So this is what we find out now, that this mass of an electron depends on the band structure, right? Depends on its energy and how it behaves as a function of k values. Okay. So so now let us try to plot this. Okay, so because E versus K you know, right? So I am plotting E versus K at the top, and at the bottom you have the effective mass, right? So what you see here, so this is the double derivative, inverse of the double derivative of E with respect to K. So you see when we plot m star along y-axis, right, and K along x-axis, right? So you see that the effective mass, right, at the inflection point, effective mass becomes infinite. Diverges, right? So, however, it is positive. Okay, but at this point, at the inflection point, the effective mass then goes to negative, right? And so beyond this inflection point, the effective mass is negative, because this you have d2e dk2. So that means what we see here is that effective mass of an electron in a solid can be positive or negative depending on the k values. So so what you see is that this is an interesting result. So mass, you never thought about mass can be negative. We know that the free electron mass, but as soon as this electron experience, so what it means is that as soon as this electron experiences periodic potential, right, so it behaves as if it has a certain effective mass, and which depends on the band structure of the electron. Okay, that means how its energetically, how it behaves as a function of k mass, effective mass depends on that. And depending on that effective mass, you show different properties of the charge carriers within the crystal. So so typically, so now positive and negative effective mass, I'll let me give you some hint towards that, right? So when electron we talk about, so if you apply a field, you know how the electron moves, right, along the field direction, right? And negative effective mass, it would mean that the electron moves in the other direction, in the opposite direction, right? If you apply a field, you expect the charge, if it is an electron, it should move along a certain direction, along the direction of the field. But for negative effective mass means that these electrons would move in the opposite directions. So depending on these kind of behavior in the solid, one talks about electrons and holes, right? So those particles, charged particles, which has negative effective mass, right? So they are called holes. So this concept I'll bring up in the next lecture in further details. So what I discussed here is basically the group velocity, how it behaves, how it is dependent on the band structure, and also the concept of effective mass, how you get this effective mass from the band structure, right? So I have decided I will make small videos, because I had problems after I recorded the full lecture. Actually I couldn't upload, or it showed several distortion at several points, so it became actually useless. I hope that this will be fine with all of you. If there is any feedback, please share with me by email. Several students have given me several feedbacks, so this will be uploaded in YouTube. Okay, all right. Okay, so thank you very much. Please go through this, look at it, look at these, and in case there is any problems in understanding, let me know. I am ready to to help you whenever you need by taking some extra additional help classes. Thank you very much.